Hello and welcome to this lecture on VLSI design. So this lecture is on static timing analysis and we will be discussing the different types of timing paths in a static timing analysis. So basically in static timing analysis we broke the whole circuit or we break the whole design into a set of paths. Called timing paths, and we calculate the signal propagation delay for each path separately, and finally we check whether there are any violations for timing constraints. So we will break the design into a set of timing paths and finally we will check if there are any timing violations for any design constraint or any timing constraint. That is the basics of timing analysis. So in static timing analysis, we are having basically four types of timing paths. First is called as data path, second is called as clock path, third is called as clock waiting path, and fourth is called as asynchronous path. So our whole design can be broken down into these four types of timing paths. Now each timing path will have one unique starting point and one unique end point. But the definition of these starting points and end points will be different as per the different types of timing paths. So if we have data path, then for data path the start and end point are defined differently. Similarly for the clock path, the start and end point are defined differently. So we are having a four types of timing paths. They are called as data path, clock gating path, and asynchronous path. So and again the data path is divided into four different types of data paths. So for example, if we take example of data path, then in the data path the starting point can be either the input port of the design or the clock pin of the flip-flop. In a data path, the starting point can be either input port of the design or the clock pin of the flip-flop. And similarly, in a data path, the end point can be either input pin of the flip-flop or output port of the design. So if you see this example, we have defined four types of data paths. So this is path 1. It is starting from the input port of the design. This is the starting point and it is ending at the input pin of the flip-flop. Then this path 2, it is starting at the clock pin of the flip-flop and ending at the input pin of the flip-flop. So the start point can be either input port of the design or clock pin of the flip-flop, and the end point can be either input pin of flip-flop or output port of the design. So again here you can see, here the start point is the clock pin of the flip-flop and the end point is the output port of the design. Then here we have path 4. So this is the simple design. Here we do not have any flip-flop. So this is the input port of the design and output port of the design. So this is also a path. So we can have four types of data paths. All these four types are defined here. In the path 1, we have it is starting from the input port of the design and ending at the input pin of the flip-flop. The path 2 is starting at the input clock pin of the flip-flop and ending at the input pin of the flip-flop. Similarly, the path 3 is starting at the input or the clock pin of the flip-flop and ending at the output port. So the start point can be either input port of the design like here or the clock pin of the flip-flop like for path 2 and path 3, and the output or the end point can be either input data pin of the flip-flop and output port of the design. So here the end point is the output port of the design. Similarly here the end point is the output port of the design, and here the end point is the data pin of the flip-flop. Here also the end point is the data pin of the flip-flop. So again, the data paths can be of 4 types. Now for a clock path, in a clock path, the start point is the clock input port and the end point is the clock pin of the flip-flop. In a clock path, the start point is the input clock pin of the design and the end point is the clock pin of the flip-flop. So in this design you can see we have this flip-flop, it is called as launch flip-flop, this is called as capture flip-flop. So two clock paths are here. So this is the clock input port of the design, the clock is starting from here. So we have the path 1 from input clock pin of the design to the clock pin of the launch flip-flop, and the second path is from the clock pin of the design, input clock pin of the design to the clock pin of the capture flip-flop. So we are having two clock paths here. Now the next type of path is the clock gating path. So here we are providing the clock through this logic gate. So in the clock gating path, the input or the start point is the clock input port and the end point is the clock input port of the clock gating element. So here you can see again the start point is the input point. So here we have this NOT gate. Here this is the starting point and the ending point is the input pin of the clock gating element. So this is the clock gating path where the start point is the input port of the design. So this is the input port and the end point is the input port of the gating element. So this is the gating element, the clock. This is the clock signal. It is fed through this logic gate. So that is why we have the clock gating path from here to here. So this is how we define the clock gating path. So finally we have the asynchronous path. The asynchronous path will start from the input port of the design and end at the set, reset or clear pin of the flip-flop. So here we can see this is a asynchronous path. So it is starting from the input port. So this is a reset button. So it is starting from this input reset pin and ending at the set, reset or clear pin of the flip-flop. So basically in a static timing analysis we can divide any design into basic these 4 types of path and finally do the analysis for all the paths individually, because as you can see all the paths have defined different starting points and different end points. So the whole design can be ultimately divided into these 4 types of paths. So please like and share the video and subscribe the channel for more such videos on static timing analysis in VLSI design. Thank you.